Hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be looking at how to calculate the chiller cooling capacity, and that is really how much cooling can the chiller produce at any given time during its operation. Now the units we're going to be using for these are the kilowatts, the BTUs and the RTs, which are refrigeration tons. Now there's going to be a few things we need to know in order to perform this calculation. So let's imagine we've got our chiller here and our centrifugal chiller. We've got the evaporator located over here, and we've got our pump, and so the return water that's coming from around the building, the return chilled water, is coming in, is going into the pump that's spinning around and pushing this off through the evaporator where it cools down and then leaves again and goes off through the building. So we're going to want to know what the volume flow rate is. Usually you can measure that from the pump. In this video we're not going to be looking at how to actually calculate the volume flow rate. I will make a separate video for that one. So we're going to assume some values for that, and then we also want to know the temperature of the water going into the evaporator and then the temperature of the water that's leaving the evaporator. Now the other two things we're going to want to know is the density of the water and also the specific heat capacity of the water. Now both of these we want to take the value at the average temperature. So whatever temperature you've got going in and coming out, when the temperature in plus the temperature out divided by 2 to get your average temperature. This is the one you want to take. Now to find the values you can simply look them up in your engineering tables and books, or you can have a quick Google and you can find it on there as well. There is a website, psoftware.de. I use this a fair bit, or I did during my thesis, but I would kind of recommend using this one. Just check to make sure you're on properties of water or steam, whatever you want to look at. Fill in the pressure and the temperature, give it a calculate, and I've run the calculation, and then what you'll see is you get your density there. These are obviously in metric units, and then you also get your specific heat capacity there. So you can take these values here. If you want to convert them over into imperial units, then another website I'd quickly use is just unitconversion.org. You can just go straight to the density converter and also the specific heat capacity converter as well. Now to do the calculations, I've split them into metric and imperial. If you're only interested in the imperial, then you can skip forward through the video to find just that section. However, if you want to learn to become a better engineer, I would highly recommend you watch through both of these so you understand the different units and how we calculate that. So first of all, straight into the metric. So first of all, the metric, we're going to assume that this pump here is producing or providing water at 0.0995 meters cubed per second, and that the water that's returning from the building, that's coming from the AHUs, the fan coil units, etc., is entering the evaporator at 12 degrees Celsius, and by the time it leaves, it's going to be leaving at 6 degrees Celsius. Now the density of the water, of the average temperature, so that's 9 degrees there, is 999.78 kilograms per meter cubed. So for every cubic meter that goes through, we'll have almost 1,000 kilograms going through. We'll also have, looking up at the specific heat capacity, you'll see it will be about 4.19 kilojoules per kilogram per Kelvin. Now the formula we're going to use to calculate this is going to be Q equals V dot times rho. The dot above the V, it just represents a rate of change, or a rate. So V represents volume, and then the dot represents a rate, so flow rate, and the rho just represents the density. So if you multiplied the volume flow rate by the density, you get the mass flow rate, which is going to be kilograms per second. So we multiply this by the specific heat capacity of the water, that average temperature, and then we multiply these by the subtraction from the water inlet temperature minus the water outlet temperature. So let's drop some numbers in there. If you remember the flow rate going into the chiller, and these figures were taken from a real chiller as well. So the flow rate into the chiller is 0.0995 cubic meters per second, and multiplied by 999.78 kilograms per meter cubed. So for every cubic meter that enters, we'll have 1,000 kilograms going in of water. The specific heat capacity was 4.19 kilojoules per kilogram per Kelvin, and we multiply that by the subtraction of the water inlet versus the water outlet. And obviously we're using the units here of per Kelvin, so we want to transform or convert our Celsius over into Kelvin. And to do that, it's very easy. We just add 273.15 kelvins. It's not a degree sign, so don't put a degree symbol there. And that will convert that to Kelvin. And you do that also for the outlet temperature. So first of all, we'll multiply these brackets, the figures in these brackets together to give us our 99.48 kilograms per second. So every second, 99.48 kilograms of water are entering into the evaporator. Next, we'll add these together so that we can work out what our Kelvin values will be. So we got 12 plus 273.15 is 285.15 kelvins, and then 6 degrees Celsius plus 273.15 Kelvin gives us 279.15. I missed the K off there, that should be Kelvin as well. So in the next section, all we do is just subtract these two together to give us a difference of 6 Kelvin. And then finally, we just multiply all three figures together to give us 2,500 kilowatts. So this chiller, given these figures and how it's running at that point in time, is producing 2,500 kilowatts of refrigeration. Now, if you want to convert that to refrigeration tons, then you just divide your kilowatts by 3.517 to give you 711 refrigeration tons. And if you want to convert the kilowatts also into British thermal units per hour, then all you do is multiply the kilowatts by 3412.142, and that will give you your BTUs per hour. So coming on to the imperial version, in order to calculate this, then we're going to use some assumed values. These values are actually from a live chiller operating at 100% maximum demand. So we've got the pump is providing water at 12,600 cubic feet per hour, and the temperature of the water going in is 53.6 degrees Fahrenheit, and the water coming out is 42.8 degrees Fahrenheit as well. Now, taking the average of these temperatures and look it up, and you'll see that the density of the water at that average temperature is 62.4 pounds per cubic feet, and then the specific heat capacity at that average temperature again is 1.0007 BTUs per pound per Fahrenheit. Now, for the imperial units, what we're going to do to calculate that is use this formula here, which is Q equals V dot times rho. The V dot is just the volume, V represents the volume, and then the dot represents a rate, so it's a flow rate. So the volume flow rate multiplied by rho, and rho just means the density of the water. So these two together will give you the mass flow rate. So then we just multiply that by the, so we just drop the figures in there. We've got our 12,600 cubic feet per hour, the volume flow rate multiplied by the density of the water at that average temperature. Then we've got our specific heat capacity at that average temperature multiplied by the inlet temperature minus the outlet temperature. So first of all, we'll just multiply these two figures here, which are in the brackets, multiply them together to give us our mass flow rate, so our pounds per hour. Then, as we've got another bracket over here, we're just going to subtract these two figures, and it will give us our 10.8 Fahrenheit. Finally, we just multiply all these figures together to give us our final BTU per hour figure, and that is the refrigeration effect. So this chiller is providing this many BTUs per hour. Now, to convert that to refrigeration tons, you just take your BTUs per hour and divide that by 12,000, and that will give you your refrigeration ton equivalent. And if you want to convert that to kilowatts, then you just multiply your refrigeration tons by 3.517, and that will give you your cooling refrigeration effect in kilowatts. So that is how you calculate your cooling capacity of the chiller, and you can apply this at any time during its operation, whether it's at part load or full load. It will be calculated like this. Okay, that is it for this video. Thank you very much for watching. I hope you've enjoyed this and it's helped you. Please don't forget to hit the like, subscribe and share button. And if you have any comments, leave them in the comment section down below. Also, don't forget to check out our website, theengineeringmindset.com. And once again, thank you very much for watching.